Welcome everyone, I'm Jim Corkins and we are now going to do examples from 3.2 voltages and electric fields. So if you haven't started those tutorials, please get started right away. Okay, here we go. We are given okay, so in this problem, what we're supposed to do in these problems is we're supposed to label the voltages on the top line here. And you're also supposed to label the distances here. And you're supposed to draw arrowheads pointing to the right or to the left to indicate the direction of the electric field, which will help you. Then we're supposed to draw a vector on this diagram for the path that was taken through your calculations. We're supposed to create an E versus R graph and solve for the electric field. So we're supposed to create this. And then we're supposed to fill this out. So when we solve for the electric field, we'll just put that answer up here. And then we'll choose right here whether the electric field is pointing to the right or to the left. Okay, so let's go ahead and work on this. So it starts off here that this voltage is -6 and it gets to +2 over +2 volts over the distance of 4 meters. But we have to note right here, this is the 0 right here. So if you look at this, this is crossing, that 0 is at the +3 mark. So that's kind of telling us where our number should go. So that's, you know what, I'm just going to put 3. This is 3, 3, 2, 1, 0, 4, 5, and 6. And so at 3, that is going to be 0 volts, and at positive, so that means to the right, it's got to be starting off at 0, which is going to be -6 volts. So at 0 meters is -6 volts. So this is going to be -6 volts. That means it's got to be dropping off by 2s here. So this is going to be +2 volts, +4 volts, and +6 volts, right? So that means let's go ahead and map out the distance, how far it's moving. So if it's starting off at -6 volts, and it doesn't matter the height, so I'm just going to put it right here. And it's going to end at +2, and it's going to cross across these 4 meters. So this is delta R. Okay, now if you look up here, the way I've labeled this is -6, -4, so it's pretty clear that the negative plate is here and the positive plate is here. And so the electric field points away from the positive and towards the negative. So we can indicate the direction of these electric field lines has to be pointing to the left. So now we know it's pointing to the left. Okay? Let's go ahead and calculate the electric field now. And we're going to use this graph to calculate it. Now, as you saw in 3.2, there was a quick, easy way to actually see our voltage is changing in the positive direction. It's changing by 2, 4, 6, 8. Again, 2, 4, 6, 8. The slope is rise over run, so the slope of this line is right here. So this is going to be +8 volts, and it's changing across 4 meters. So the slope of this line, which is not exactly the electric field, is +2 volts per meter. But you have to remember, again, that delta V is equal to negative E dot delta R, right? And so right here, delta V over delta R is equal to negative E, and then so multiply that negative against both sides, and you get this. So we just solved for we just solved for delta V over delta R, which we found out to be positive 2 volts per meter. But we have to multiply it against a negative. So the electric field is going to be equal to a negative 2 volts per meter. Okay? So negative 2. And so what that's saying is the electric field is a constant electric field. So this is kind of like the first problem, one or two problems on your first page. Okay? Let's go on to another one that we did in 3.2, but similar to one of the problems that is on your homework. Here you're given a voltage that starts off at 0 volts, and it looks like it's dropping off to negative 6 volts across 2 meters. And then it looks like it just stops, and for 1 meter, it's a constant voltage. So that's kind of interesting. So if we think about this for a second, it starts off at 0 volts. So it's at 0 volts at 0 meters. So the initial position is right here at 0 meters. That's the 0 volts, 0 meters. And it's going to be moving to the right. And when it hits 2 meters, so I'm going to just count 1, 2. I guess I should mark that. It's at negative 6. And it looks like it's crossing negative 2, negative 4. So I'm going to say this is negative 2 volts, negative 4 volts, and negative 6 volts. That means this has to be positive 2 volts, positive 4 volts, and positive 6 volts. And this has got to be negative 1, negative 2, and negative 3. Okay. So numbering this is important. It actually makes you think about how the problem is laid out. Now, since the positive voltage is here, you know these are the positive are built up here, the negatives are built up there, and so we know the electric field is going to be pointing to the right. So the electric field is pointing to the right. All right, so let's go ahead and plot this. So at 0 volts, it gets to negative 6. So I'm going to choose one of these things. I'm going to start off at positive 4 heights, and it's going to move over here to negative 6 volts. So that's the delta R on that first problem. So this is the delta R here. And then something happens, and it just stays right at that negative 6 volts for 1 meter. That means it has to be moving upwards with a separate delta R. That's interesting. So this delta R path is right there. So let's plot the slopes of each one of these things. Let's do the black one first because that's really simple. That slope is 0, so that voltage is 0. There's no electric field pointing upwards. That's kind of what it's saying right there. Interesting. Now, For this guy, it's dropping by 246, so this is -6 volts. It's dropping across 2 meters. So this is going to work out to be negative 3 volts per meter. But, like as we learned right here, we have to take the opposite of that. Okay? Because we just worked out that the electric field should be pointing to the right. This is saying that the electric field is pointing to the left, and it can't be. So again, we got to do, E is equal to the negative of delta V delta R, which is going to be negative times -3 volts per meter. So that's going to work out to be a positive 3 volts per meter. So now that makes sense. That aligns with our rightward pointed electric field. And then we plot it on here. Positive 3 is right here. So this is going to be, you know what? I used red for that guy. So this is positive 3 right there. And then something happens, and then our path changes, and now it's 0. Okay? So I think you have a problem kind of like this. All right. Again, doing these, you're really getting a really good understanding of how electric fields, paths, and voltage are all working together. Okay? Let's move over here. We got 2 pages left. They're not very difficult. Okay. On mine, it says this. Using the information in the E versus R graph, the initial voltage is -12. So initial voltage is -12. Let's do this, -12. And we have to figure out everything from here. Okay, well, if you look at it, the electric field is -2 volts. So I'm going to write that here. And that means the electric field has to be pointing to the left. So I'm going to go ahead and mark those here. Which means this is the negative plate, and this is the positive plate. Okay, now let's figure something else out here too. If you look at this area right here, that area relative to that -2 mark, that is the total change in voltage. Okay? And again, go back to that video in 3.2, but this area right here is the total change in voltage. And what I mean by that is delta V is equal to -E dot delta R. That is this. Whenever you see -E dot delta R, if we saw delta V over delta R, that's a slope. But if you see -E dot delta R, that is an area. Okay, so this is -2 relative to that 0. Okay, so the area I'm seeing is -2 volts per meter times 6 meters. So E, the electric field E, and I don't mean -E, it's the electric field, is -12 volts. Not electric field. The change in voltage is -12 volts. So this is the change in voltage, right? Now, we just determined that E is -2 volts per meter. So another way of solving this is we put this in here, right? So we have the negative, and then we're going to have to multiply that by the -2 volts per meter, and then multiply this whole thing by 6 meters. So we got a negative times negative is positive. So this is going to also work out to be, so this is going to work out to where the actual change in voltage is positive 12 volts. Okay? Because you got to remember, we have to take the opposite. When you go from here to the electric field, we're taking the opposite sign that we worked out. Going back, we have to also do the opposite side. All right, so we know the end place is going to be somewhere across 6 meters. We're starting out at -12 volts, but we're increasing a total of 12 volts. That means our voltage is changing to this. There we go. Now let's write that path on our place here. Well, I'm going to just start off saying this is 0, 1, 2, 3, 4, 5, 6. And our -12 volts is here. And we're dropping off to 0. And so I'm just going to put positive 12 volts over here. And we're just going to go right to it. We don't need to fill the rest of these in if we don't need to. So dropping off to 0, and that is delta R. Okay. So this is similar to your third page in your tutorial, or third or fourth or something like that. But this is similar to one of your problems in your tutorial. Okay. The last one we're going to do is an example, which I corrected since the problem I did in 3.2. I corrected the angle so we get whole numbers. The path that we're going to take is delta R right here. Okay, so it says that this is a 45-degree angle with the negative y-axis, so that's the angle 45 degrees. If you look at it, we're actually moving down and to the right, right? This is the path that we're taking. If you also notice that this distance right here is 2, 4, 6. So this is 6 meters displacement, okay? And we have the angle 45 degrees. So given this, now we have to remember only this part, if we're traveling straight downwards, we're not changing voltages. Only this guy right here, this is the important guy. That is the one responsible for the change in voltage. So whatever this works out to be, that is our change in voltage, okay? Which is going to help us figure out the electric field stuff, okay? So let's go ahead and do this. We have a distance here. We have 45 degrees. So we need this distance. We know it's changing from positive 8 volts to negative 4 volts. So we know it's starting off at positive 8 volts. And then over some distance, it's going to end up at negative 4 volts here somewhere. So let's figure that distance out. Well, I have to figure out this right here. So this is the opposite side of the angle 45 degrees. And I have the adjacent side. So I need to figure out the opposite. I have adjacent. Adjacent over opposite. Opposite over adjacent, that's tangent. So tangent of 45 is equal to opposite over adjacent. So multiply both sides by that 6 meters. and we get this. So the opposite side, we're going to work that out right now. 45 degrees, 45, second function tangent is 1. So this is going to work out to be 6 meters as well. So this is across 6 meters. Okay. 1, 2, 3. So this is, so maybe let's count by twos. This has got to be 0, 2, 4, 6, 8 meters. Actually, I could have just started, you know, you can choose to place 0 there if you want. But I'm just going to go with this because I'm stuck with it now for my distances. So we know it starts off at positive 8 volts, and at 6 meters away, it's going to be at negative 4 volts. So this is going to be our graph. Okay, let's figure out that slope. So it's dropping by 1, 2, 3, 4, 5. So dropping by 5. So that's negative 5 volts. Oh, no, I'm so sorry. Not by 5. 2, 4, 6, 8, 10. So dropping by 10 volts across 6 meters. Okay. Let's figure out what that looks like. I think yours are all whole numbers. Mine is the only one that's really weird. So that's going to be negative 1.67. But you got to remember your electric field is opposite this slope. Again, for multiple reasons, we determined that. So this is going to be positive 1.67, which makes sense because the electric field has got to be pointed to the right. So the electric field is pointing to the right. This is the plate with the negatives on it. This is the plate with the positives on it. Okay, there we go. So negative 1.67, that's about 2. So it's pretty close to 2, just under it. I'm going to draw my little graph right here. There you go. Actually, this is half. Yeah, actually I was right. It's not quite 2, but pretty close. So there you go. So hopefully this helps you. And again, you're practicing really important skills. And if you could do this, you will be excellent. Thank you very much.